Welcome to AP Calculus BC. Today is day 1, and we're going to be doing limits and properties of limits. So let's get started. So I've prepared 2 prompts for us to start off with. We're going to define what a limit is, and we're also going to write the notation. So limits are useful in calculus because they tell you what value a function approaches instead of what it actually is. So if we think about, let's say we have a function of like f of x. When we plug in x, we get what the value is at x. But what if we wanted to know the behavior? I'll write it down. The behavior at x instead of what the value is. Because sometimes f of x cannot exist, or maybe it's just undefined sometimes. And so a limit, if we want to, like, the formal definition is the value a function, this is a key word, approaches at an x value. And so you may be saying, oh, what does this have to do with, calculus? You shouldn't confuse this with what happens at the point, but around a point. Or in other words, it's the behavior of the function of the point. And so the notation, if we want to find like what f of, let's say we have some variable c that we want to see, we can plug in f of c to see what's happening at the function. But if we want to find the limit or what the value is approaching at an x value, then we can say the limit as x goes to c of f of x. And so these aren't necessarily the same thing, and so we gotta watch out for that. Okay. I've gotten 4 graphs, and I've also labeled them at c. So we'll keep using the variable c in this case. And so it looks like this is a logarithmic function. This one is a rational function. This one might be a sinusoidal function, and this one's just a piecewise function. And so if we look at what's happening as we approach c in this one, sorry about that. As we approach c, it looks like So as we approach c on this first graph, for instance, it looks like we're reaching some value, and I'll call this value L. And so I would say the limit as x goes to c of f of x is L. And I'll say this function is f. And so in this case, we actually found out that f of c is also L. So the limit of a function at x equals c can also equal f of c. How about this function over here? If we take the limit, or as we look on the left side, for example, it looks like we're approaching infinity. How about the right side? If we approach from the right side, it looks like we're approaching negative infinity. So in this case, we would say there is no limit because the function is not really reaching any point. So I would say it does not exist. Similarly, if we do plug in f of c, we don't really get an answer. So I will also say do not exist. Or I guess the better word would be undefined, because it's an asymptote. The third one, we have a sinusoidal function, and we have a hole at x equals c. And so, but if we use the behavior, we can see that it's approaching some value. You can see, like, if we filled it in, you could see that there's some value there. And so if we call this value L, then we can say the limit as x goes to c of f of x equals L. But if you plug in f of c, it does not exist or is undefined. And so you can see why limits are useful, because we can find out what a function's behavior is without needing it to be defined. How about this one over here? This one is a little bit different because it is a piecewise function. And so if you approach from the right side, it looks like it approaches some value, let's use new variables, m. And if we approach it from the left side, we get a value of n. And so the way you would write this is the limit as x goes to c, as x goes to c, and on the number line, this is the positive numbers, and these are the negative numbers. So you can imagine like going from that and going from that. You could say, well, oops, why is it not undoing? You'd say x goes to c from the positive side of f of x is m, while the limit as x goes to c from the negative side of f of x is n. And as you can see, if we just take the limit as x equals c, you can see that there is no limit. So the limit as x goes to c without any symbol of f of x does not exist. But if we do plug in f of c, we can see that it is m in this case. So here are 4 situations in which a function can equal its limit, or a function at x equals c can equal its limit. A function cannot exist and its limit. When the limit exists but the function does not exist. And when the limit does not exist but the function does exist. And so I want to revisit this third one just to say that if the point were somewhere up here, for instance, and I'll call this P, for example, then we could say the limit as x goes to c of this new graph that I just drew of f of x would still be L, because we're still checking what is happening near this function at x equals c, which it looks like it's approaching L from both sides. But f of c in this new graph would equal P. And so it doesn't matter what is happening or what f of c actually is. The limit only cares about the behavior near c. And so if we follow the graph, it looks like it's approaching L from the left and the right side. But if we plug in f of c, we'll get P. Okay. Let's get started. We have 2 limits here. We have the limit as x goes to c of f of x equals L, and the limit as x goes to c of g of x equals m. I just wanted to clarify that these letters I'm using, so C, L, M, in the previous problems I used like P, these are all constants. So as we're approaching some x value, and I'm just using C, we'll approach a value of L. So there are actually some like properties. If we're working with these more abstract forms of limits, then there are some properties of limits that we can use. So let's start with the easy one. So we have the limit as x goes to c of some function k times f of x. Then we can actually rewrite this as k times the limit as x goes to c of f of x. So what I did there was I pulled the constant out, and therefore if a function is being multiplied or divided by a constant or some number, then you can actually pull out the number. And so in this case, we can rewrite this as k, and the limit is L. Now, what if we have the limit as x goes to c of f of x plus g of x, and I'll put brackets to emphasize it. Then we can actually rewrite this, instead of the limit of the sums, we can do the sums of the limits. So we can do the limit as x goes to c of f of x plus the limit as x goes to c of g of x. And so the way I like to think about this one is I will just take the limit of each of these individually. And so in this case, we actually know what this equals. This is L and this is M. The next one we need to worry about is subtraction, and luckily enough, it's the same thing as addition. So I can rewrite this as plus or minus. So I can do f plus or minus g of x is equal to that. So, and the same thing over here. This implies that the limit of the differences is the difference of the limits. And so this is always true for limits. And similarly enough, we actually have the limit as x goes to c of f of x times g of x. And so similarly, the what is this called? The quotient, or the multiplication, in the limits becomes the limits of the multiplication. So we can rewrite this as the limit as x goes to not f, of c of f of x times the limit as x goes to c of g of x. And in this case, we actually know what these are. They are L times N. And if you guessed it, yes, the limit as x goes to c of f of x over g of x is the limit as x goes to c of f of x divided by the limit as x goes to c of g of x. And there's only one stipulation, and it's that the limit as x goes to c of g of x cannot be 0. And I think you can see why that's the problem. It's because if this were 0, then we can't divide by 0. And so you'll have to keep that in mind. And there's one last one that you have to know, and it's the limit, I'll use g of x this time, the limit as x goes to c of g of x raised to a power, so I'll put it in brackets, let's say n, is the limit as x goes to c of g of x to the power. And so this is equal to, what is it, m to the n. And I forgot to answer this. Eventually this leads to L over n. And so these are our 5. I like to think of these as like reversing it. So instead of doing the limits and then multiplication, you do multiplication and then limits. Or instead of doing division and then limits, you do limits and then division. So you can go this way, or you can also go this way. And similarly here, instead of taking the power and then taking the limit, you can take the power, or you can take the limit and then take a power. And so that helps because we only know what this value is and not this value. And so it helps to simplify, and then we can get the answer. And so let's put this into action. I prepared for us 3 problems. This is also linked in the description if you want to follow along. It's a worksheet, and it says to use properties to find the limits given that the limit as x goes to 9 of f of x is 6, and the limit as x goes to 9 of g of x is negative 1/2. And so we actually have real constants this time with 9, 6, and negative 1/2. We've also got some pretty complicated limits that we can break down using our skills that we just learned. And so let's start with A. So A says the limit as x goes to 9 of 7 f of f, the limit as x goes to 9 of 7 of f of x minus 8. And so let me just rewrite it. So it's A, the limit as x goes to 9 of 7, I'll just keep it, f of x minus 8. And so the first thing I'll usually do is the big picture. And so it looks like there's something minus something. And so I'm going to rewrite this as the limit as x goes to 9 of 7 of f of x. And here's the key part. We're going to subtract the limit as x goes to 9 of 8. The next step is I see this constant here, the 7, and I want to bring it out to the front. So then the next step will be 7 times the limit as x goes to 9 of f of x minus the limit as x goes to 9 of 8. And so we can actually solve this from here on. This 7 stays the same, and we actually know what f of x is at x equals 9, or the limit of it at least, and it's 6. And then we can subtract. This is a little complicated or tricky to think of, but if you want to think of it as 8 as a function, which is just a straight line, so let's say we had y equals 8, I'll even put the arrows, then if we checked the behavior at x equals 9, then we can see that it's still 8. So this is just 8. And also we can what is it called? We can find a pattern to this. So the limit as x goes to c of any constant n is n. So that's just something nice to know. So if we resolve this, this is 42, I think, and subtracting 8, and that, I think, is 36. So that's our final answer for part 1, or part A, I mean. let's start part B. Part B states the limit as x goes to 9 is equal to the square root of -3 times f of x times g of x. And so let's rewrite this one down here. So what was it? B, the square root of -3 f of x, g of x. So let's start with the biggest picture. We need to get rid of the square root. Oh, oops, I forgot to write the limit. Sorry about that. The limit as x goes to 9 of the square root of -3 f of x, g of x. Well, the square root can also be rewritten as the limit as x goes to 9 of -3 of f of x, g of x to the 1/2 power. And so by doing this, we can actually push this out. So we can say this is equal to the limit as x goes to 9 of -3 f of x, g of x, all to the 1/2 power. Isn't that useful? Now we can actually pull this 3 out from the limit. So this will become -3, just take the whole constant out, times the limit as x goes to 9 of f of x times g of x. I'll even emphasize the times to the 1/2. Can't forget that. And now we can use that multiplication rule, and we can say this is equal to -3 times, I'm going to put this in parentheses, the limit as x goes to 9 of f of x times the limit as x goes to 9 of g of x, all to the 1/2 power. And so let's go up here. So it looks like the limit of as x goes to 9 of f of x is 6. So I'm just going to rewrite this. So this becomes 6. And this, the limit as x goes to 9 of g of x becomes -1/2. So -1/2. And all to the 1/2 power. And so 6 times 1/2 is -3, and it's also multiplied by -3. How convenient. And so that will result in, 9 to the 1/2. If you really want to rewrite it, that's the square root of 9, and it's easy, that's 3. And so our final answer is 3. Okay, let's do the very last one. The limit as x goes to 9 of f of x plus 2 over g of x to the 4th power. So how are we going to solve this one? Let's break it down. So let's rewrite it over here. In fact, let me check C, limit as x goes to 9 of the entire function, of f of x plus 2 of g of x to the 4th power. And so right off the bat, let's get rid of this exponent. So we can rewrite this as the limit, in fact, I'll write my brackets, as x goes to 9 of f of x plus 2 over g of x to the 4th power. Now, I see some addition inside this limit, so let's break it up. And so I'll rewrite it as the limit as x goes to 9, don't forget my bracket, of f of x plus the limit as x goes to 9 of 2 over g of x to the 4th power. Now, I think we can resolve most of this, although we still have some division over here. So let's rewrite it as the limit as x goes to 9 of f of x plus this becomes the limit as x goes to 9 of 2 over the limit as x goes to 9 of g of x to the 4th power. Let me put equal signs there. And so now we just need to evaluate this. It seems that we actually got all the parts, and so we can actually use this rule that I wrote down here to resolve that. And so that is equal to the limit, actually let's just plug it in. So the limit as x goes to 9 of f of x is 6 plus Well, the limit as x goes to 9 of 2, if we follow this, it's just 2. And then the limit as x goes to 9 of g of x is negative 1/2 to the 4th power. And so now it's just some arithmetic. 2 divided by negative 1/2. If you really need to, you can rewrite this as the reciprocal of this. So it's negative 2 to the 4th power. And so 2 times negative 2 is 4. Negative 4. Whoops. Negative 4 to the 4th power. And that's equal to 2 to the 4th power. And if you simplify that, that is 16. So our final answer is 16. We have concluded this day 1 of using properties. Tomorrow, we're going to be using other strategies to solve limits that don't involve just addition, subtraction. They're going to be a little bit more challenging. And so this is just a nice introduction to limits. I hope you enjoyed, and goodbye.